So the idea is, Beryl asked me to talk to you about the polarization of light. Now the first question that comes to mind is, what is light? Which actually may be the most difficult question of all. There may come a time that you come to MIT, that you go to college, and that you're going to take courses in physics. And in your freshman year, you will go through a course which we call 802. 8 stands for physics, and 2 is the second course in your freshman year. It's offered in the spring. And when you take that course, you may have an idea afterwards what light is about, but not quite. Then in your sophomore year, you take another course, which is 803. And you may have a better idea what light is about, but not quite. Then in your junior year, when you're a physicist, you take 2 more courses on quantum mechanics, 804 and 805. And once you have taken those 2 courses, you have no idea what light is about. And that's the case with all physicists. All you will know then, how to manipulate those difficult equations which predict exactly what light will do. And that's the only objective of a physicist. But if you ask me, do you understand what light is? I will have to say, no, I really don't. But I have the advantage that I've taken all those courses. And so I can make a prediction about what will happen if we do what. And if I showed you any one of those equations which are behind this, all of you would walk out right now, and that's clearly not the idea. So the idea is today that we will concentrate on a somewhat simplified picture, which is not wrong. And that picture is that light is a wave. And that was first introduced in the 17th century by a Dutchman with the name of Christian Huygens. Actually, a Dutch person would pronounce it as Huygens, but you don't have the ui in your language, and you don't have the ch, let alone that you can say Huygens. So we will just call it Huygens for now. And so Huygens introduced the idea that light is waves. And we now know, but we didn't know that, of course, in the 17th century, that light propagates with an incredible speed of about 200,000 miles per second. So the light from the moon would take about 1 second to reach us, and the light from the sun would reach us in about 8 minutes or so. So I mentioned the idea that light is a wave. What do we know about waves? Well, you take a pebble and you throw the pebble in the water, and you see water waves. The water bobs up and down, and in fact, the wave also propagates, just like light waves propagate. The water waves will propagate at a much lower speed than light. But something is moving. There is an oscillation of some kind. Now, in the case of water, I can see exactly what is moving. I know that water is going up and down. How about now light? Well, that is more difficult. That's why you have to take all those courses, and then you still don't know. But I can tell you what we call them, although that doesn't give you much information. We say a light wave consists of, now hold on to your chair, don't fall off it. It's an electromagnetic wave. It doesn't tell us much, does it? All we know is it has something to do with electricity, the same kind of stuff that powers all these lights, and it has something to do with magnets, magnetism. Here, this is a magnetic brooch. Stick it on, it's a magnet. And light has something to do with electricity as well as with magnets. For now, we will forget about this idea that we don't fully understand what light is, and we even forget about the idea that I gave it this difficult name, namely electromagnetic waves. But what I would like to do is to give you some feeling today for what a wave is and for the bizarre behavior of light, particularly when you are going to polarize that light. And you will understand exactly what that means by the end of this lecture. Let's first look into the idea of a wave. And for that, I would like some assistance from someone. Oh, wonderful. Now, there's one thing you have to know. If you're going to help me, everyone in the world may see you 6 weeks from now. If that's okay with you, that's fine. If it's not okay with you, then you should go back.
I can do this.
It's okay. Is it okay with your parents? Also okay. Wonderful. Now, you hold this end, and you walk back. Go there. Actually, yeah, because I don't want you to run into the table. Just go lower, yeah. Okay, and just walk back. What is your name?
Lee.
Lee. Wonderful name. Walk back, Lee. Keep walking back. Don't let go, huh? Lee, keep walking back, yeah. Walk back. Oh, you're doing great. That's fine. That's enough. So this is a spring. And if I wiggle my hand up and down, remember water was moving up and down, and then the water waves would propagate. If I move my hand up and down, also a wave will move in her direction, and it may reflect and come back at me. That's okay. Light can do that too. Light can reflect off a mirror. So look at a wave. It is a wave. You see it move? Oh, you shouldn't shake. You're not allowed to do that. Of course you can. You look, there's a wave traveling. It's a traveling wave. Hold it now for a minute. No, not shaking now. Yeah. Notice that I was shaking my hand up and down. And so the wave would stay in this direction, up and down. But I can also shake my hand left to right. Look what I can do. And that now is the basis behind the idea of polarization. If the wave is going only in this direction, we in physics say this wave is linearly polarized in this direction. You may want to forget about that word linearly, but this direction don't forget, because I'm going to repeat that many times during this lecture. And when I shake it like this, then it's polarized in this direction. But I can also shake it at an angle, like so. Now it's polarized in this direction. And so now, thank you very much, Lee. You did terrific. You did incredible. Thank you very much. Does it hurt? Does it hurt?
Yes, my finger hurts.
Well, you have to sacrifice for science sometimes. This was the first time in your life.
I like science.
Yeah, so do I.
In my 4th grade classroom.
You coming to MIT?
No.
Oh.
I don't live near here. I live sort of far. And when I go to school, I'm in 4th grade. I study science, and I'm really good at it. My friends say I'm a genius at science.
It's terrific. But maybe you will change your mind and you may come to MIT. Can you help me again? Okay, Lee? So we know now about a wave, even though it was in a spring. It wasn't light. But we get the idea that you can make it oscillate like this. You can make it oscillate like this. You can make it oscillate in any direction that you would like to. And so, if I now think of light coming straight to you, so you would be at the end of the spring and seeing it coming to you, then some of those waves may come to you and you would see the spring go up and down. The light is now coming to you. A little later it may go like this, and some of it may be like this, and some of it may be like this. Each individual one would be polarized. This would be polarized in this direction. This one would be polarized in this direction, and traveling towards you. And the next one may be polarized in this direction and traveling towards you. But if I look at all the light together, some of it polarized in this direction, some in this, some in this, and some in this, there is not one direction which is preferred. All directions occur. And that's what we call unpolarized light. So I'm going to write this down in big letters. That is very important that we understand what is unpolarized light before we will understand what polarized light is. So unpolarized light. is this. This alone would be 100% polarized. If all the light that came to me was doing like this, 100% polarized. If all the light was doing like this, 100% polarized. If all the light is coming to me and oscillating like this, 100% polarized. There are several ways in physics that we can change unpolarized light into 100% polarized light. And when you look around here in the classroom, all that light from these light bulbs, from the fluorescent tubes, the light from the sun, all of that is unpolarized. And we are going to convert it into 100% polarized. And there are three easy ways that we can do that. The easiest is that you buy yourself what we call a linear polarizer, of which you have two. If you open the envelope, you have two of them. It looks like a little plastic plate. This is that plate, enlarged. And it is cut in such a way, I will take this off because we don't need this, not now. And this plate is cut in such a way, you can cut it in many cases because you buy these large sheets. It's cut in such a way that if light, unpolarized light, goes through this plate, that it's 100% polarized what comes out in this direction. And I believe that all these plates have been cut that way. But I cannot be 100% certain. I can't vouch to that. It's possible that some of them are like this, but I don't think so. I think all of them will be like this. So that means if light comes from the back and reaches you, then after it has gone through this plate, all the light is going to come to you as this. That's one way we can make linearly polarized light, and that's the first thing we're going to look at. Then there is another way that we can make linearly polarized light, which I will also discuss and demonstrate, and that is by reflecting light off glass or off water. And there is a third way, which is more difficult, and that is if we have fine dust particles and we shine the light onto these fine dust particles, the light will be thrown in all directions. It's not a nice reflection like you have of a mirror. And we call that scattering. And I will show it to you. And that's also a way that you can make polarized light. But let's first now turn to these polarizers, which were invented by Edwin Land, who founded the Polaroid company. Although the idea that you can make polarized light out of unpolarized light was already known in the 17th century. But they didn't have these fancy, nice Edwin Land plates. If this plate were what we call an ideal polarizer, ideal polarization, an ideal polarizer, then it would mean that if you shine unpolarized light on it, that 50% comes through, so the light is reduced in half, but everything that then comes through is linearly polarized. So a certain light intensity goes in, half of that comes out, but it's all linearly polarized. That's what we call an ideal polarizer. In reality, you never get 50%, you get always something less. But think of it as being an ideal polarizer to get a picture of what these plates will do. So what I want you to do now is take one of these plates, close one eye, and hold the plate in front of one eye. And hold it like this. All the light that you will see now is linearly polarized in this direction. Is this an exciting experiment? No, because you can't see it. Your eye cannot see linear polarized radiation. Animals can, some animals can, not all. Bees can. They can see linearly polarized light. They can know in which direction. But at least I want you to look through it and imagine in your head that everything is now polarized 100% in this direction. And then I want you to put the plate like so, now all the light that comes through is now polarized in this direction. And then I want you to put the plate like this, and now all the light that you see is polarized now in that direction. In fact, some people can see the direction of polarization, but that's a different, it takes a tremendous amount of training. Most of you cannot. How can it be that this unpolarized light going through this piece of plastic, that everything comes out like this? That is mind-boggling to imagine what's going to happen. And I agree with you, that is not easy, and that's why most physicists will say, we really don't understand light all that well, but we can predict what will happen. If I go back to my spring, when the spring was oscillating like this, imagine that as the spring was I was shaking the spring up and down, and the wave went like this. Imagine that I would make a slot like this. Piece of wood here and a piece of wood there. That wave could go straight through the slot. There would be no problem at all. Here would be that slot, and this wave could go straight through because it moves up and down in the slot. But now imagine that I have light, that I oscillate in this direction. The spring oscillating in this direction. So now it oscillates like this. I'm trying to make you see this in a three-dimensional way. It comes here. Now it hits this narrow slit, can't go through. It gets stuck. So here you see that with this spring, you can easily see why this light, which is polarized in this direction, goes through, but light which is polarized in that direction cannot go through because the slot is too narrow. And in that sense, you can perhaps now imagine why unpolarized light can be changed into linearly polarized light. I'm just mentioning this so that you have some idea on what may be going on in that plate, even though that idea is not absolutely perfect. Now there is something that I have to teach some of you, although many of you may know this, what comes. But I'm going to need this for the rest of my lecture. And that is the idea of an angle. What is an angle? And how do we express angles? If I have here a circle, and I draw here a line, and I draw here a line, then we call this an angle. And how do we measure an angle? In mathematics, we have adopted, that's a definition. There's nothing that you can understand about it. It's just the way we name things. We call an angle that goes all the way around, so that is what we call a full rotation. So this leg goes all the way around. This angle then we call 360 degrees. Is it logic? No, I would prefer 100 degrees, but we call it 360. I can't help it. That's the way it's called. It's called 360 degrees. Now you think of it, there are 60 minutes in an hour. Equally absurd. Why not 100? Why not 10? Equally absurd is that there are 60 seconds in a minute. Makes no sense. Equally absurd, there are 12 inches in a foot. Why not 10? I don't know. All these things are historical, and we have to live with that. So once you define this angle as 360 degrees, then you now know that 1/4 of a rotation is going to be 90 degrees. And so I'm going to make there a picture of 90 degrees, since we're going to need that very badly during this lecture. So if I rotate this leg over 1/4 of a rotation, then it will be like this. And this now is 90 degrees. It's 1/4 of a rotation. And this 90 degrees, we have another word for that in math. We call that right angles. So this we say, this hand, this arm is at a right angle relative to my other arm. It's the same thing as saying they are at 90 degrees relative to each other. It's all the same thing. We also say one is perpendicular to the other. That's the same thing. 90 degrees, right angle, perpendicular to, it's all the same thing. And as the lecture goes on, I may use perpendicular, I may use 90 degrees, I may use the word right angle. And when it is a right angle, we even put in there often a little square like that. We don't do that in any other angle, only when it's 90 degrees. So this angle would be 180 degrees. And this angle, very close to 45 degrees, if I divide this exactly in two, and so on. So now, you should know what an angle is. If I now come back to your two polarimeters, and you put one in front of your eye, then all the light that comes out, if you hold it like this, is polarized in this direction. But suppose now you put on top of that the other like this. What do you think you will see here? Where the two are at 90-degree angles relative to each other, where the two are perpendicular to each other, what do you think you're going to see? Yeah? Absolutely nothing. Darkness. Good for you. And why is that? Well, if the light first comes out this way, then this second polarizer would only be willing to let the light through if it is oscillating in this direction, because that is the direction in which it's willing to let the light through. But there is no light that oscillates like this. And so all the light that comes out here gets stuck in this one and nothing comes through. And so now you see why we gave you two polarizers. So you can now take those two plates and you can hold them in front of one eye and rotate one relative to the other, changing that angle slowly. You can first make the angle 0 degrees. That means you put them both in the same direction. Light will go through. And now when you make the angle larger and larger, you will see less and less light. And when they are at 90-degree angles relative to each other, you will see complete darkness. So try that. Can you see me? Yeah? Good. The light that comes from my face is completely unpolarized. Hold one polarimeter in front of your eye and rotate it, and you will see that no matter how you rotate it, you will not see any changes in the light that comes from my skin. Maybe from my glasses, but not from my skin. Do we agree? Okay. But now, I'm going to change that. I'm going to hold in front of my face this linear polarizer. Now, all the light that will come to you from my face is now polarized in this direction. Now, with one polarimeter in front of your eye, rotating it, you can make me go away. Now, of course, if you cannot see me, I cannot see you either. So if you hold your polarimeters like this, you should see me. If you hold them like this, you should see nothing. And if you do something in between, you will see some of Walter Lewin, a little bit, but not all. It's a little dimmer. Yeah? So now you see the idea of what polarimeters can do. The experiment that you just did with your two polarimeters in front of your own eye, I can do here too, of course, with a light coming from this light source. And I can put a line on here. MIT is not going to like that. There's the line. And I can put one polarizer on there. So you can obviously see through it. The fact that the light is now polarized, we don't see that. But now comes my second polarizer, and I put it right angles, and the light is gone. Then you don't see the line anymore. Because this is doing exactly what I was trying to explain. They're now at 90-degree angles. And if I make the angle different from 90 degrees, then you will see the line again. Not very bright, but you will see the light. And if I put them in the same direction, then you'll see the maximum that you will ever see through these two plates. So I assume that you now have an idea of what happens when unpolarized light goes through your polarizer. Now, one of the things that you will learn if you take physics at MIT or anywhere else for that matter, you will learn how much light will come through the combination of these two, depending upon what the angle is between the two. So if they are in the same direction, and if they were ideal polarizers, then 50% would go through. If you do it like this, nothing goes through. But you will also be able then to predict what happens at 10 degrees, at 20 degrees, at 30 degrees, and so on. And that was already discovered in the 19th century by Mr. Malus, and that law is named after him. And we call that Malus' law. But I will not go into that in any detail. But we can predict exactly, not only at 90 degrees that nothing will come out, but we can exactly predict how much light you will see if you rotate. But keep in mind that even if I rotate them at an angle which is not 90 degrees, if this is my first polarimeter, so the light comes through to you from behind here, it's polarized like this. If I put the second one then in this direction, then it will always be linearly polarized in this direction. That does not change. The only thing that changes is that the light that comes through here is then dictated by Malus' law. Malus will tell me how much light comes through. But it is, of course, non-negotiable. It must be in this direction because my second polarimeter will only let light through that oscillates like this. So that's not going to change. So far, so good as far as your polarizers are concerned that we handed out. Now, I want to go to the second way that we can make 100% polarized light if we start off with unpolarized light, and we do that through reflection. You can do that by reflecting the light of water or glass or plastic or paint, not metal. If you bounce light off metal, you will not be able to polarize it. And you will see later that that's indeed the case. So here is a plate of glass. And I have some light that falls onto that plate. I make a nice beam of light. Could be sunlight. We will use these light guns for that. And so some light falls onto this plate. A nice beam of light coming in from some lamp here. We always use as a reference line a line which is perpendicular to the surface. Perpendicular, I use that word, 90 degrees angle. This line is my reference line, is 90 degrees relative to the surface. And we call this angle in physics, something you may forget, angle of incidence. If this is glass, not all glass will do it exactly the same way, but garden variety glass that you have at home in your windows, and if this angle is 55 degrees, then the light that is reflected in this direction is 100% polarized. Not at all obvious why that is, but it is 100% polarized. This angle here is the same as that angle there. That's always the case. When light strikes glass, it bounces off just like a billiard ball bounces off the edge of the table. We would say then the angle of incidence is the same as the angle of reflection. This angle is the angle of reflection. And some of that light goes into the glass. In fact, most goes into the glass, but that is not polarized. It is really only the light in reflection that is 100% polarized. If you were to look into this light beam, so here is your eye, and you see the light coming to you, so here's the light beam and it's coming to me, then I would see all this unpolarized light coming to me. Remember? Something like this, something like this, something like that, something like that. And the ensemble is unpolarized. If I look here into that light beam, after it is reflected, so it comes up to me, it's now 100% polarized in this direction. And I will demonstrate that to you. And the angle of 55 degrees depends a little bit on what kind of glass you use. Could be different, could be a little larger, could be a little smaller. If this is a water surface, the angle would be 52 degrees, which is not so different from 55 degrees. I have here a glass pane, a pane of glass. For those of you who cannot see it, here it is. And I can rotate that. I can rotate it like this. And here I have a light gun. So light, I'm going to strike onto this piece of glass. Most of it will go through. You will see it there. I don't want to know about that. That's not going to be polarized. Some of it will go in this direction. That is the light that is reflected. And you're going to see it on this center screen. And I can change that angle. I can make the angle close to 55 degrees, in which case the reflected light will be practically 100% polarized, but I can make the angle a little smaller than 55 degrees or a lot smaller. And when I do that, then we have a situation that the light is partially polarized. Partially polarized. What that means is that a lot of it comes out like this, a lot. But there may be also some like this, and some like that, and some like that. But if the dominant amount is in one direction, we call that partially polarized. If everything is in one direction, we call it 100% polarized. And at that 55-degree angle, it is very closely to 100% polarized. If the angle is not exactly 55 degrees, it will be partially polarized. So we're going to have this light beam. Let me first turn on the light so that I know what I'm doing. It must come out somewhere here. You will see it shortly. Make it completely dark. Oh, by the way, you think, of course, that with your linear polarizers, you will be able to see that the light that hits here is 100% polarized. And the answer is you can't. And the reason for that is that as it comes off this glass, it is polarized. But when it bounces from this screen back to you, it loses the polarization. So you cannot see it. But that's why I have here a linear polarizer, which I'm going to hold into the beam. So we're going to turn all the lights off, make it dark. And let's see whether we can... There is the light beam. So this is the reflected light. And there you see the light that goes straight through on the wall there, which I'm not interested in. Most of the light actually goes straight through this glass. Only a small fraction is reflected. So this is the light that is reflected. I can see it now. Look into the reflected beam. So the angle is now not optimum. I put the angle there somewhere at random. And I will show you that if I hold this large sheet of polarizer, into that beam, and if I rotate it around, you will see that the light intensity of the top part is changing. Here it is. Just keep an eye on it. Now it's darker, but it's not completely dark, but it is darker than in this, right? That's clear. It's darker. So it's partially polarized, because it's not completely dark, the upper part. This is as good as I can do. But now I'm going to make the angle closer to 55 degrees, which is about here. And we're going to do it again. So this is the top part. And now I'm going to rotate my polarimeter. And now, look at that, look at that. It's almost completely dark now. Now, I may not be exactly at 55 degrees, and that's not so interesting for me because it may take a long time to get it there. But you see now that indeed this light is very close to 100% polarized. Whereas if I hold the polarimeter like this, the light goes through. And it's simply by one reflection of the glass. So you know a lot. You know what linearly polarized light is. You know what partially polarized light is. And you know that you can make linearly polarized light by using your polarimeters. And you know that you can also make it by bouncing, reflecting light off a surface, like glass or water. Here I have a piece of glass. You can't see it, but believe me, it's there. And under that piece of glass is a word written in very large letters. And when I turn on this light, and I stand here, and I want to read that word, I can't read it. Because that light source reflects in the glass. And if that were the sun, I couldn't even keep my eyes open. It would completely blind me. I can't read that word. But when that light bounces off here, and it comes out here, it may not be 100% polarized, but it may be almost 100% polarized if the angle is close to 55 degrees. So now what I can do, I can hold in front of my eye a linear polarizer, and then I may be able to read that message, that secret message that I cannot read now. No, I can't read it. I have no idea what it is. Ah, now I can see it. Now I can't, but now I can. Why can I see it now? Because the light is polarized like this, and with the polarimeter, I kill that light. And I want to show that to you, although that is not an easy demonstration. We have here a television camera. And the television camera is going to look at this word. But with the lamp on, you will only see a glare of light. And then I'm going to hold in front of the camera my polarimeter and rotate it. And I will kill the light, not all of it, by no means all of it, but a large amount of that light, I can kill it because I know it's polarized like this to a large degree. And so if I hold my polarimeter in the right direction, I can kill this light. And so the glare from the glass will go away. At least will be highly reduced. Oh, I have to turn on the camera, which is here. Ah, you see, you can't read the message. You can't read. All you see is this big white spot that you see is the glare, the reflection. Imagine, it could be the sun, you're driving your car. Your parents drive the car. Or you're out in the snow, you look in the direction of the sun, and you see this incredible glare in front of you. But now, you have this polarizer, and you're going to rotate in front of this polarizer. And it says hi to you. That's all it says, hi. That was a nice message. So what I've done now with this linear polarizer, I kill a lot of the reflected light, so now you can see what the message is, whereas now you cannot. And the reason why I show this to you is that now you begin to see the idea behind polarized sunglasses. Why do people wear polarized sunglasses? And how would you put those directions of polarization in your glasses? If there is the sun, and there is water on the road, and the sun reflects this awful light in my direction, then it is partially polarized in this direction. And so, when I have sunglasses, what I do not want to do is put the polarimeter in like that. That would let the light through. That would be the worst thing you can do. You would send your polarized glasses back to the manufacturer and say, the hell with it, I don't want those. But what you do want, you want your glasses to be like that. Because now, the glare of the road, whether it is the sun bouncing off water, whether it is the sun bouncing off snow or ice, makes no difference, always is to a large degree, or maybe totally polarized in this direction. Always parallel to the road. So this is what you want to do. Do any of you have polarized sunglasses on you? You do? You're not sure whether they're polarized. That's easy to check, sir. Take a look at them. Nope. Oh, you think yours are polarized? Oh, boy. Nope. But mine are. Mine are linearly polarized. And it just so happened this morning that they broke. Which is bad because I have to go to California today and I will need them. But one arm came off. But if I put these sunglasses on, it says hi. If I take them off, I can't read the message. My sunglasses are like this, and the polarization is like this. I can give some of you my glasses and try it, but the problem is these are prescription glasses. So if I gave you these glasses, you wouldn't even know where you are. It would be like you were walking on the water, so I can't do that. But what I can do is show you here that indeed the direction of polarization is exactly as I pointed out. Here are my sunglasses. You see that line through the sunglasses? And now I claim that this is the preferred direction of polarization, and this is the preferred direction of polarization of these pieces that you have. So this way, you should kill the light, and that's exactly what's happening. You see nothing now. You cannot see the line through there, but if I rotate this like this, then you should see some light through. I can see some light through. So I've demonstrated to you that my sunglasses are indeed designed in this direction. And so if you have some at home, you can test that because you now have your linear polarizers and you know in what direction those little plates have been cut. All right, so that was reflection. Let's see what is next. I have given numerous times at my exams, when I was lecturing here, this famous course 802 that I mentioned to you, which is called Electricity and Magnetism. It's the name of that course. Remember, light was electromagnetic waves, so clearly when you learn about electricity and magnetism, you will learn about light. I have asked numerous times at exams, I give them 5 pictures. And in one picture I do this, and in one picture I do this, and in one picture I do this, and I ask the student in what direction should they be polarized. And you get all kinds of answers. But some of them have it right, maybe for the wrong reasons. So it is a standard question on our exams. I now want you to look through your linear polarizer at all the objects that we have here around in the room and on the table. There is no strong sunlight that will blind you out. There is no beautiful 55-degree angle. Everything is at random. But if you look very carefully and you rotate your linear polarizer very slowly, you may see, looking at the glass spheres, that you will be able to change the reflected light. And if you look at metal spheres, you will not see that. So do it very slowly, and we put glass spheres here, and here, and some metal there, there is some metal here. And it depends on where you sit. I can see it very clearly. Some of that light from the fluorescent tubes bounces off at approximately the right angle, and so then it becomes partially polarized. It will not be 100% polarized because the angle is not exactly perfect. You are sitting at random locations, and these objects are randomly placed. It's not as nice an experiment as I did here with this plane of glass. Who can actually see, when you rotate them, you clearly see that the light intensity of the glass objects changes, but it doesn't change when you look at the metal. And if it does change when you look at the metal, then I can tell you why. It is possible. It is possible if the metal is very close to the glass, when the light bounces off the glass, it becomes partially polarized. And then it bounces off the metal, it remains partially polarized. But we try to set them up in such a way that that's not going to happen. If at home you want to test, looking around, of the reflection of the paint, maybe of the kitchen table, you may also try this on the mirrors that you have at home. Keep in mind that a mirror has an aluminum backing, which is metal. So if you look into a mirror and you think you're going to get polarized light, you won't succeed. It's only the light that bounces off the surface of the glass, but not the light that would bounce off the bottom of the mirror, which is the dominant amount of light, which bounces off metal. So light of a mirror is not linearly polarized, even if you make the angle just perfect. Now, when you look at a rainbow, you see a rainbow in the sky, and that makes us all feel very good. It's a wonderful thing to see a rainbow. Here's a rainbow. Nice rainbow. There's a rainbow in the sky. If you take your polarizers that you now have, you will be able to see that the light that comes from this part of the rainbow is almost 100% linearly polarized in that direction. You will see that when you come out and when it rains and when there's a beautiful rainbow in the sky and you take your polarizer and you rotate it, you will see that the light is polarized in this direction. And here it is polarized like so, and here like so. It is polarized, as we say, tangential to this arc. So here it is polarized like so. Why would that light be linearly polarized? Well, that's a good question. And that is something that is not part of this lecture, but I will want to give you at least an idea where it comes from. And then I will demonstrate it to you. The rainbow is formed when sunlight enters water drops. Could be a waterfall, could be a garden hose, could be rain. It enters that water drop. Say it comes in like here. When it enters it, it changes direction. In the back here, some of it reflects. This is water, and this is air. It can reflect of that transition, just like water, like light can reflect of air to glass, and then it comes out again here. And it is this trajectory, which I have not explained to you, but it is that trajectory which is responsible for the formation of the rainbow. And it is here where the reflection occurs that the angle of refraction is almost perfect for the transition from water to air. If this angle were 37 degrees, it would be perfect. It's almost 37. It's actually 40 degrees. It's very close to 37. So it is right here in the back of the raindrop that the polarization occurs. Now, some of you, before I demonstrate the polarization of the rainbow, some of you will say, well, why do we see colors? Well, that's more than I wanted you to tell today, but it is not an unreasonable question. Why do you see colors? If you look at the sun, or the moon for that matter, then that light doesn't look very much colored at all. In fact, if anything, you may want to call that white light, maybe yellowish white light. But that light contains many colors, surprising as that may be. And if you take a piece of glass that has this shape, which we call a prism, and if you shine a beam of light in here, then as it comes out, you will see all those colors. You will see red here, and you'll see blue here, and you see some green in between, and all other colors. You will see red, orange, yellow, green, blue, violet. All those colors you will see. But yet, you look at the sun, it looks white. This glass object is able to decompose this white light into these individual colors. This is something that I want you to see first, before we get into the rainbow. Here is such a prism. And here is a beam of light. It's not the sun, but it is very white, that light. Strikes this prism, and it's right there on the wall will make a prism. We call it a spectrum. It will make a spectrum on the wall. You will see red, green, blue, yellow, orange. If you're ready for that, I can try that, and I'll make it very dark, so you can see that spectrum on the wall. There it is. So the white light, once it goes through this glass, decomposes into many colors. Those colors must have been present in the white light. You can't create them out of nothing. So it decomposes that light because of the shape of the glass. Why is it that we don't see colors when we look at the sun? Why does it look white? Well, that's the way that your brains function. Your brains are strange. And when you bring all those colors on top of each other, your brains tell you it's white light. Whether your brains tell you the right thing or not, I don't know. But you see white light when you bring those colors on top of each other. It is the glass prism that makes them come out in different directions, so that some of the red comes on the left side, and the blue goes on the right side of the wall. That's why you now can see the individual colors. But if I were to merge those colors, then you will see white light. So that's why you normally don't see them when you look at the sun or when you look at the objects here in this room. Your brains are very strange. So are mine. You can see all these colors here, can you? You see red, green, blue, and violet. Why do you see red here? Because there's only red coming from this part. So your brains see red. Why do you see green here? You see only green because your brains say that's green because there's no other color coming from that. If I rotated that disk very fast, your brains will get so confused because they will see the colors coming from one location, all the colors simultaneously. and you will see white light again. And so that's what I will do next. And first we'll get some light on that. There it is. And now I'll make it dark in the room so that not completely dark, but almost dark. And then I will spin that very fast. And you will see that your idea of colors is going to fade away. You're not going to see colors anymore. Which proves my point. If you see colors from the same direction, all the colors, your brains fool you. Your brains say, hey, that's white light. So you see that? This is not part of polarization. This has nothing to do with polarization. But I want you to understand that a water drop is a little bit like a glass prism, except that it doesn't have this shape. It has this shape. But these different shapes can make the colors, can separate the colors, can decompose the colors, and that's what's happening with the rainbow. And so now what I will do for you, I will make for you something like a rainbow. It's not exactly a rainbow, but it is something like a rainbow. And I will do that with one water drop. Because if I made it rain here in 26100, you would never come back. So we can't do that. So we have one water drop. There it is. It's in a little glass sphere. And we're going to shine an enormous amount of light right into your face. Hits this water drop. And some of it will reflect off the back and will come back. And you will see here an arc, which will be red on the outside, blue on the inside. You will think you see a rainbow. And it is indeed very similar. Now I can't shine this light into your face, so I have to put a cover over it, otherwise you will not come back either. You end up in the hospital. Okay. Now, the light on this screen will be extremely faint. What do you expect? I use only one water drop. And let's face it, how much did you pay for this lecture? Right? You can't wish for everything. So it's going to be extremely faint, but it will be polarized. And I will show you that it's polarized along the arc. You cannot use your polarizers, because once the light hits here and it comes back to you, it loses the direction of polarization. Maybe not for 100%, but almost. I will give you 30 seconds for your eyes to get used to the darkness. If I don't do that, you won't see anything, because it is very faint. And then I will show you with my polarimeters that when you see the arc here, that I can rotate it around, and I can just in the right direction kill that light of the arc or let it through. All right, so the first thing, your eyes have to get used to the darkness. Oh, there's some light on there, which I can turn off. So give this a little bit of time. Nice for the video cameras. Okay. Now, there is your arc. Can you see it? Yeah, just say yeah if you can see it. Okay. Do you see that it is red on the outside and bluish on the inside? That's what the rainbows should be. So, I argue now that if you look right at the top there, that the light is polarized in this direction, but almost 100%, and here it is polarized in this direction. Here is my sheet, my polarimeter, and notice that I can let all the lights through now in the middle, and I'm going to rotate it, And now I kill that light. And that is convincing proof that that light is highly polarized. Almost 100%. I can do the same here. I let the light through this polarimeter. This is apparently for this sheet the allowed direction of polarization. And I rotate it very slowly. It gets darker and darker. And now it's completely dark. Almost nothing goes through anymore. Have you seen this? Yeah? So the light, the rainbow, highly polarized. Also the white light inside there. Just below the rainbow you see some white light. You also see that in nature. That light is also, notice, nearly 100% polarized, because that white light also goes away. Now, from now on, you will always carry on you a linear polarizer. You simply cannot go out on the street without a linear polarizer. I always have in my wallet at least one linear polarizer. And whenever you see a rainbow, you take this linear polarizer and you make sure that that bow is polarized. And maybe the day will come that it is not polarized, in which case you should call me right away. Always carry on you a linear polarizer. Now I come to the third way, the last part, that we can polarize the light. Not by means of reflection, but remember I mentioned fine dust particles. Light strikes fine dust particles. It doesn't reflect in the nice way that it bounces off glass, but it scatters in all directions. A little bit goes off in this direction, some in this, in different directions. We give that a different word. We call that scattering. And when light scatters off fine dust, it can also become 100% polarized, provided you do it just the right way. We have a beam of light coming from below. Later, that's where it will come out. Here is light. The beam of light will come straight up. And we will put dust particles in here. And those dust particles have to be extremely fine, for which we will use cigarette smoke. As much as I hate to smoke, I will have to do that once. And if these small dust particles are here, then some of this light, which comes up, changes the direction, not as nice as it will do off the glass that it reflects, but some of it will go in this direction, some in this direction, some in this direction, some in this way. And some will come to you. Some of it will go to you. And if this light that came this way is scattered over an angle of 90 degrees, it's 100% polarized. Why? Forget it. That's not important. I just want to show you that it is polarized. How can we be sure that you will see the scattering over 90 degrees? Well, all of you are almost in perfect condition, because the light comes up like this, and so if it goes in this direction, no matter whether it goes there, or there, or there, or there, the change in direction is almost always, no matter where you sit in the lecture hall, 90 degrees. Do you follow that? It goes from this to this. That's 90 degrees. This to this is 90 degrees. This to this. So all of you are almost in an ideal position to see that light that was scattered off my smoke particles. And it will be polarized. If I draw a circle here, if you're sitting here in the lecture hall, it will be polarized like this. If you sit right in front, it will be polarized like this. If you sit a little bit there, it will be polarized like this for you like this, and for you like this. So I will make an attempt to demonstrate that. But there is something that I have to tell you first. You get that for free. Just like the colors with the rainbow, you get them for free, and I don't want you to miss that. And that is that if the smoke particles are very small, that the violet and the blue light are way more likely to scatter than the red and the orange. That's not so easy to understand, but you have to take my word for that. Therefore, if my smoke particles are very small, that smoke will look bluish, because the light comes up, and it is the blue and the violet that likes to be scattered. The red doesn't like to be scattered, it goes straight through. But the blue likes to be scattered, so you will see that smoke bluish. You may have seen the exhaust of cars sometimes, bluish. People who burn oil coming out of the exhaust, it looks bluish. Same reason. It's the sunlight that scatters off the small oil particles, and it looks bluish. So we're going to catch two birds with one stone, namely, I am going to have this beam of light coming from below, and then you will see that the light is blue, and you will also see that the light is polarized, for which you can use your own polarizers, and the polarization will be in this direction, this direction, this direction. Before I do that demonstration, I want to show you two slides. And the first slide is the slide of stars, a very famous cluster of stars called the Pleiades. And those stars are embedded in a huge cloud of very fine dust. And if I can have the first slide, you will see that. There you see these bright stars, and there is dust around them. And look at this color of this light, which is scattered. The light comes from the star, scatters off the dust, comes in your direction, and it's blue. Because the probability, the chance that blue light scattered is way larger than red light. So you see that here in nature, right in front of you. The next slide. You see a man on the moon. Now there is no atmosphere on the moon. So if there is no atmosphere, then the sky would look very dark. But this person is walking on the moon and is scuffing his feet, and there are very small dust particles which go up. And here you see that the light from the sun, which comes from the right side, that goes in your direction, looks bluish. Because these are very fine particles, and the blue actually is the color that likes to scatter. And I will get back to this, because that's the reason why our sky is blue. And if it scatters over 90 degrees, the light would be polarized, but that you cannot see on this picture. So now we're going to do this smoke demonstration, for which you can use your own polarizers. So the idea being that light comes from below. I'm going to turn that light on. Oh yeah, thank you. Thanks, Marcos. There's the light. And I have to get some cigarettes going. I'll make it very dark. Ah. Yucky. Okay. So we're going to get some smoke in here from these cigarettes. Now I know that some of you will say, that's not blue. Well, that's your problem. I call that blue. And before this demonstration is over, you will also call it blue, believe me. Try to see, if you rotate your polarimeters in front of one eye, that you can change the light intensity of this smoke. And it should be consistent with the idea that it is polarized in this direction. Who can clearly see, if you rotate the polarimeter, that the light intensity of the smoke clearly changes? Just say yeah. Just say no if you don't see it. Ah, you don't have the courage to say no. So I've convinced you, this comes out, almost all of it in 90 degrees. It comes up here, and it goes in this direction, is 90 degrees, that is 90 degrees. All of you are almost sitting at 90 degrees. Now I will convince you that the color is blue. And the way I will convince you of that is that the color is only blue or bluish if the particles are very small. If the particles are much larger than what I would call very small, then the blue light is no longer preferred. That means the red light, the yellow light, the green light, and the blue light all are scattered in the same way. So what do your brains tell you? That's white light. Your brains are being fooled. Your brains see all the colors simultaneously, and they say that's white. Is there a way that I can make these particles a little larger and show you the color change from bluish to white? And the answer is yes. All I have to do is something that is awful. Hold the smoke in my lungs for maybe half a minute. And then the water vapor in my lungs will precipitate on the dust particles of the smoke, and therefore they will grow. And if now I puff out the smoke, there will be very small water drops in that smoke, but they are much larger than the smoke particles, and you will clearly see that that light that reaches you, that has been scattered now off the smoke that was in my lungs, is distinctly wider than this blue. So if you're ready for that, just remember first this color. Okay, there we go. You see the color change? So it was blue the first time. I mentioned the sky. The sky is blue. Yeah, the sky is blue for the same reason that the smoke is blue. Namely, in the Earth's atmosphere are many very small dust particles. And even if those small dust particles were not there, in the atmosphere itself, there are small fluctuations of the density of the air. And so if I put you at the bottom of the Earth's atmosphere, which is a big blanket of air, and you're here, and the sunlight, say, comes from here, from this direction. The sun is very far away. Sunlight strikes the atmosphere, coming in like so. If you look straight into the sun, that's a stupid thing to do. There's where the sun is. Straight there where the sun is. Terrible. Don't do that. Look there. What do you see? How can this light ever reach you? It scatters. It scatters off these fine dust particles. So what is the color? Blue. Because blue is preferred scattering. Blue and violet are the ones that scatter way more than red and orange. So when you look right there in the sky, looks blue. Looks blue. Looks blue. That's the reason why the sky is blue. The same reason why the smoke is blue. Is it possible maybe that some of that sunlight that scatters off the dust in the sky scatters at 90 degrees? If that's the case, I'm in business. I go with my little polarizers, I look at the sky, and I can convince myself that that part of the sky must be 100% polarized. Of course, there's a whole ribbon in the sky, no matter where the sun is. As long as the sun is above the horizon, there is a whole plane in the sky, which is always 90 degrees away from the sun. If the sun is there, this is all 90 degrees away from the sun. If the sun is there, this is all 90 degrees away from the sun. Just like this angle here, 90 degrees. And so, if I look at the sky, not only is the sky blue, which I now perhaps understand a little better, but if I look at the direction which is 90 degrees away from the direction of the sun, no matter where I do that in the sky, with my little polarizer that you have now in your pocket, you can convince yourself that the sky is 100% polarized. Why are sunsets red? So beautiful. Well, that you should be able to answer now for yourself. If the sun is very low at the horizon, and you are here, and here is the blanket of air, and the sun is very low at the horizon, the sunlight comes in this way. Because the sun is so low in the sky, this is the direction of the sun. So imagine how much atmosphere this light has to go through. And remember, the blue light is the light that wants to scatter. And then there comes a time that all the blue light has been scattered out, that there is no blue light anymore. Well, then maybe some of the green light will start to scatter. And then maybe some of the yellow light will scatter. And when all these colors have been removed from the white sunlight, what remains is red. And so it is the light that penetrates very deep into the atmosphere, that makes it all the way to here, that has no blue anymore in it, no green, not even yellow. And it, therefore, is red. And there happens to be a cloud here, specially made for us, and so the cloud looks red, because that red light strikes the cloud. And so, therefore, the same reason why the sky is blue is the reason why the sun is red when it sets. Because all this sunlight now must go through an enormous layer of atmosphere. And the blue light is gone, and green light is gone, and what you end up with is red light. This is what is left over, maybe some of the orange. And that is what I want to demonstrate to you as my last demonstration. So I want to catch, with my last demonstration, I want to catch or kill 3 birds with 1 stone. And the 3 birds that I want to kill are, number 1, that the sky is blue. So I'm going to make a blue sky for you. Number 2, that if you look at the sky 90 degrees away from the sun, that the sky is 100% polarized. And number 3, if we make this atmosphere huge, that the sun becomes red. All 3 I can demonstrate to you in 1 demonstration. And I'm going to do that as follows. Here is a bucket, small bucket, with something in there which is called sodium thiosulfate. I don't know what it is, so you don't have to know what it is. But that's what it's called. Sodium thiosulfate. Here, I'm going to shine in white light. It comes from this gun there. Here, see this white light. And I'm going to put in here, when the demonstration starts, a little bit of sulfuric acid. And you get a chemical reaction, and the chemical reaction in this bucket will make sulfur precipitate, which are teeny, weeny little parts of sulfur, which will slowly precipitate. And when these small sulfur particles in this chemical reaction are produced in the atmosphere, this will turn blue. And you know why? Because why do you see light? Because the light has to scatter. And the blue light is preferred over the red. So you will see that your sky, small as it is, will turn blue. If you sit here, you can move a little bit later there because it's tricky to see it. So you will see it blue. For some of you who are at 90-degree angles, which are only those prefers people, so Adrian, you are just sitting at the right location, that light is 100% polarized too, because it comes in like this, and it goes like this, that is 90 degrees. Not for you. It will be partially polarized for you. For you, it will be 100% polarized. Polarization is in this direction. Light comes in, scattered, it's blue for all of you. For you here, 100% polarized in this direction. You can use your own polarimeters to convince yourself of that. But then as time goes on, more and more sulfur will precipitate. And so what do you think will happen with this beam of light that goes through here? What do you think will happen with the color of that beam of light? Almost right, but not quite. Think about what the atmosphere will do. The atmosphere removes the blue. It becomes redder. Exactly. So this becomes red and redder and redder and redder. That's exactly what happens during sunset. When the sun is still this far above the horizon, it looks a little bit reddish, but it's not so fantastic. But it goes farther in, gets redder and redder and redder. And that's exactly what you're going to see with this light beam, which we're going to produce there. I will first throw in the sulfuric acid, because the whole experiment will take a few minutes. Then I know for sure that the sulfuric acid is in there, and that I don't get it on my skin, because that's very awful. Okay, so the chemical reaction is starting, and so you get your polarimeters out, and I have to turn on the light source. It's on. I have to turn off all the light. And now the fun begins. Make sure you can see the atmosphere, which is that bucket. And already I can begin to see the color blue. There's no question. That light that goes through there is bluish. And if you're in the wrong position of the lecture hall, just move yourself to a better position. Try to come a little closer to the center. Also convince yourself, for those of you who are sitting right in front of me, near 90 degrees, that that is almost 100% polarized. And I can use my polarimeter to show that to those who are not in an ideal position by rotating this. Now the light goes through, and now that reflected beam is almost killed. Depends on where you sit. You see the difference? But use your own polarimeter. You should be able to see that. So your sky is blue. If you're at the right angle, you see that it is nearly 100% polarized. I am here, ideal position. Incredible for me. I cannot see the reflected beam anymore now. But now I can. Now I can't. Hey, look at the beam at the end is beginning to turn a little reddish. You see that? That the beam itself already is exhausted of all its... I look at the sun. My goodness, that is going to be some sunset. You've never seen a sunset like this. Most of you should already begin to feel a little romantic when you see such a sunset. What a great sunset this is going to be. A blue sky. Sky is 90 degrees. Scattering 100% polarized. You can impress your friends with this, believe me. If you're out on the beach and you see a sunset like this, you take your polarizer out, and you can show that the sky in certain directions is 100% polarized, and you can even tell why the sun turns red. We are going to be close to sunset, I think. Boy, is that red. Oh, that's red, all right. Ah, we must be very close to sunset now. Yeah, I knew it. There goes the sun. All right, I hope you enjoyed this lecture. Thank you. Okay, Beryl, I don't know what your plans are, but I can answer some questions if necessary. Where's Beryl? You have questions? Yeah?
Towards the end of it.
Speak a little louder, yeah?
How come towards the end of the reaction it started to get greener?
Greener. Right here, you mean? Well, to me it looked a little bit redder. Maybe others saw it greener. The redder part I can fully understand, because as the light enters the bucket here, so much of the blue is thrown out that already this beam turned, for me, a little bit reddish. I mean, here it was completely red. So it's completely red here. I wouldn't be surprised that it is a little reddish here too. If you saw it greenish, well, then you may have seen the idea that this was all gone and this was all gone, and so the beam that was left over was a combination of red, orange, yellow, and green, which may have made a little bit of a greenish impression on you. To me, it would look more reddish. But it should change the color as it does. As the beam gets deeper into the atmosphere, it turns. That's the reason why the clouds turn red. So when you were on this side of the atmosphere, it turned reddish. Oh, there's Lee. I'll come to you in a minute, yeah?
If you were to stick a prism, stick light through a prism and then another prism, would it change back?
Man, you are fantastic. You should come to MIT. That is the experiment that Newton did for the first time, and that made him famous. Indeed, if you take a separate prism and you put it next to your other prism, the colors become white again. You are fantastic. So that means if you do this experiment and you put a second prism like this, these colors become white again. A+.
Well, I see sometimes the sunsets are sort of red, orange, and yellow, and I was wondering why that one didn't turn red, orange, and yellow, because I've seen sunsets that are red, orange, and yellow, and sort of with a little mix of purple and stuff.
You saw it purple.
Sometimes it's a little mix.
Yeah, well, you see, if you mix various colors, your brains can do strange things. And if you pick random colors here, your brains can see very different colors than the individual colors. And if somehow your brains tell you that you saw purple, I believe you. I never saw purple, but it can happen, yes. Maybe your brains are very special.
Special?
I think you have very special brains.
Well, I am creative and I draw a lot, but it's probably that I get mixed up.
Probably.